Still see me, still hear me, still see whiteboard.
Yep.
Okay, fantastic. All right, so let's give this a try. So this is our practice final that we're going to be going through for Physics 121. Let's start with the concept questions. My plan is just to go straight through it, but if you have any questions along the way, please stop me and ask any questions that you have. If I'm not being clear or if I've said something that doesn't make sense to you, please ask questions. Otherwise, I'm just going to continue cruising through it, okay?
Perfect.
All right, so number one, the value of the angular momentum of a system is the same at a later time as it is at an earlier time, only if what is true. So this is getting at conservation of angular momentum. So in order for it to stay the same, we're saying that it's conserved, it stayed the same value. So when does conservation of momentum or conservation of angular momentum apply? So we know that conservation of momentum is something that we usually do with collisions or interactions between two objects, but that in order for momentum to be conserved, there has to be no net external forces acting on our system. If there is an external force, then we'd use the impulse momentum theorem instead of conservation of momentum. Now, the same idea applies when we're talking about a rotational system, but instead of talking about net external forces, we'll talk about the rotational version of that, and that's net external torques. So conservation of angular momentum applies anytime you have an interaction or a collision between objects within your system and there's no net external torques. And looking at our choices, it says only if there is no collision. Well, that's not true. We usually use it for collisions. Only if there is no inelastic collisions. No, that's still not true. We usually use it for collisions. Only if there is no change in momentum of individual particles. Well, anytime there's a collision, the individual particles will exchange momentum. So they will change momentum. So that's not it. Um, Internal torques acting. Well, as long as they're internal, they're part of the system. And the reason they don't matter to us is if they're internal, then both the action and the reaction, according to Newton's third law, will both be part of our system. And so when we add it together and do the net torque or the net force, they'll cancel each other out. So it's actually answer E, the net external torques acting on the particle of the system. If there's any external torques, then we only get the action and not the reaction as part of our system. And so they're unbalanced torques, and those are the ones that are going to change our angular momentum and make it so that it's not conserved. So the correct answer here is E. All right, number two. Two cylinders made of the same material roll down a plane inclined at an angle theta with the horizontal. Each travels the same distance. The mass of cylinder B is twice the mass of cylinder A. In what order do they reach the bottom? And the answer is that they reach the bottom at the same time. And I just jumped to this right away because what we know about objects rolling down inclines, is that this is generally a conservation of energy problem. In this case, we don't have any collisions. This is just one object moving from one location to another location, from one height to another height. And as it does so, the potential energy it has at the top of the hill, the gravitational potential energy, the mgh it has, is going to be transferred into kinetic energy as it rolls down the hill. So it's going to be changed into translational kinetic energy, which is 1/2 mv squared. And in the case of round objects, it will also be transferred into rolling or rotational kinetic energy, 1/2 I omega squared. Now, when we did these example problems in class, we found that the gravitational potential energy had mass in the equation, mgh. That translational kinetic energy had mass in the equation, 1/2 mv squared. And that our rotational kinetic energy also had mass in the equation. Now, the equation was 1/2 I omega squared, but the I, the moment of inertia, was always something like mr squared or 1/2 mr squared or 2/5 mr squared. It always had an mr squared in it. And as a result, it also has mass, which means that every term of our equation has mass in it. So the masses always cancel out. So the fact that these two cylinders have different masses doesn't matter at all because the mass cancels out of the conservation of energy equation. The only thing that matters is the shape of the objects. And since both of these objects are cylinders, they have the same coefficient to their moment of inertia. They're both going to be 1/2 mr squared. And that ultimately is going to decide what speed it has when it reaches the bottom. So they both reach the bottom at the same time. Number three. As an object moves from point A to point B, only two forces act on it. One force is non-conservative and does negative 50 joules of work. The other force is conservative and does 30 joules of work. Between A and B, what happens to the kinetic energy and the mechanical energy of the system? So the two energy theorems that relate energy to our system is we have the work energy theorem. And the work energy theorem says that the total work, the net work, the sum of all work being done on a system equals its change in kinetic energy. So if we want to know how the kinetic energy changes, all we do is we add up all the work done together and get a total for the work. In this case, we're told that we have two different forces and thus two different work terms, a negative 50 joules of work and a positive 30 joules of work. That means the net work is negative 20 joules. That net work has to equal our change in kinetic energy. So it tells us that our kinetic energy will decrease by 20 joules. So our kinetic energy is going to decrease. Now, when we talk about the mechanical energy, that's where we're talking about conservation of energy rather than the work energy theorem. And we found that energy is conserved, or mechanical energy is conserved, as long as there's no non-conservative forces that are doing work on our system. Non-conservative forces doing work causes our energy not to be conserved. So of the two works that we were given, there's only one that is non-conservative, and that's the negative 50 joules of work. So the total mechanical energy is going to decrease by 50 joules because we have that one non-conservative work being done on it. So again, the mechanical energy will also decrease. So in this case, the kinetic energy and the mechanical energy decrease. That's answer B. All right, number 4. To decrease the intensity of sound you are hearing from your speaker system by a factor of 12, what can you do? All right, so intensity of sound. So this is the equation where we had that the intensity was the power over the area. And the area, generally when we talk about sound, it's moving out in a spherical wave. So it's power over something like 4 times pi times r squared. So this is the equation that we're talking about in this problem. And so if we want to decrease the intensity by a factor of 12, we need a combination of the power term and the r term to give us that factor of 12. And notice that the r term gets squared. So as we look at this, if we look at answer A, for instance, reduce the power by a factor of 3, and then increase your distance by a factor of 4. So if we take that distance factor of 4 and we square it, that gives us 16. Times 3 is going to give us 48. That gives us a 48 factor in the reduction of the intensity. That's not what we're looking for. We're just looking for a reduction of 12. So we're going to have to go through each of these options looking for one that when we do the distance squared and we multiply it by the power, we get 12 out. Now, luckily for us, that's going to happen right away on answer B. So on answer B, reduce the power by a factor of 3. And then increase your distance by a factor of 2. So when we square the 2, we get a 4. Multiply that by 3, that gives us 12. That is, in fact, the factor we're looking for. And so B is the correct answer. Though you can go through and verify that C, D, and E do not work as well. Okay, so far so good?
Mm-hmm.
All right, number 5. A rock is thrown at some angle above the horizontal with a certain velocity. It reaches its highest point and then starts to fall back down. What is the velocity of the rock at the highest point of its trajectory? All right, so this one is kind of a trick question, or what you guys would call a trick question. We've gone through a lot looking at the motion of objects and what happens when they reach their tippity top. Let me remind you that when we throw something straight up at the very top of its trajectory, its velocity will instantaneously be 0. Its acceleration, on the other hand, will not be 0. Its acceleration at the tippy top will still be 9.8 meters per second squared downward. But this one actually asks us not for something that's thrown straight upward, but something that's thrown at an angle. And when you throw it at an angle, its velocity at the top is not going to be 0. Its acceleration at the top is still going to be 9.8. But remember, when you throw something at an angle, gravity changes the vertical component of the velocity, but it doesn't change the horizontal component. Gravity doesn't pull us left or right. The acceleration in the x direction is 0 for these two-dimensional kinematics problems. And as a result, whatever initial velocity you have in the x direction, you're going to continue to have that x velocity throughout the entire problem. So at the tippy top, your y velocity goes to 0, but your x velocity stays constant. And so at the top, it is equal to its initial horizontal velocity. Answer C. All right, number 6. Consider a hoop of radius r and mass m rolling without slipping. Which form of kinetic energy is larger, the translational or the rotational kinetic energy? So we want to compare these two equations. So for our translational kinetic energy of translation, that's just going to be 1/2 times m times v squared. And for our kinetic energy of rotation, that's going to be equal to 1/2 times I times omega squared. And in this case, in order to compare them, we need to plug in what our value is for I, the moment of inertia, based on the shape of our object, and what our value for omega is. So we're still going to have the 1/2. Oops, that's not 1/2, that's 1/2. And then we're going to multiply it by I. And in this case, let me look back at the problem. This is a hoop rolling without slipping. So for a hoop, if we look up the moment of inertia of a hoop, that's just going to be mr squared. And then we multiply that by omega squared, and omega is just v divided by r. So when we do that, what we get is that the r squared in the numerator here cancels with the r squared in the denominator. And so what we get here is just 1/2 times m times v squared for the rotational kinetic energy, the same as what we got for the translational kinetic energy. So in this case, they are both equal. Notice that that's only true here because of the shape of this object, because it was a hoop, because we put in mr squared. If we put in 1/2 mr squared or 2/5 mr squared, we would get a very different result and they would not be equal to each other. So be aware of that.
And on the test, will we have what the moment of inertia is equal?
Yes, so on the instruction page of the test will be the same equation sheet you see on the practice final. And that practice final page, I hope, has it on here. Let's take a look and see. If not, it will certainly be added on. And you're right, I don't see it on the practice final version. So I will make sure that I put that on here to add on to make sure that is on your test. So yes, you will not be expected to memorize or to derive those in the exam for common shapes. Okay. All right, so that is number 6. So moving on to number 7. The amplitude of the motion of a simple harmonic oscillator is doubled. By what factor does the frequency of the oscillator change? So what we learned in our simple harmonic motion section is that the frequency and the amplitude are independent of each other. The period or the frequency, we had all those equations for them. Like for instance, if we had the period of a mass hanging from a spring, it was something like t equals 2 times pi times the square root of m over k. And if instead we had a pendulum, for instance, then it was something like t equals 2 times pi times the square root of something with L and G in it, right? All of these equations for the period, none of them have the amplitude in it. So it didn't matter how far back you stretched the pendulum, or how far back you pulled the mass before you let it go. We did a couple of labs that dealt with that. It still had the same period of oscillation and thus the same frequency. So the frequency or the period is independent of the amplitude. And as a result, the oscillator change should be a factor of 1. It doesn't change at all. And that's answer C. Number 8. 2 boxes, one more massive than the other, rest in contact with one another on a smooth level floor. A horizontal force, capital F, pushes on one or the other of the boxes. The contact force between the 2 boxes is larger when which way is the force applied? So let's make a little sketch of this one. So we have a floor over here, and we're going to have 2 blocks, a large block and a smaller block in contact with each other. And then we're going to apply a force to one side or the other. So perhaps in the first case, we put the force over here on this side, like so. And then perhaps on the next instance, we put the force over here on this side instead. And the question is, when we put these different forces onto it, which one is going to result in a bigger force of contact in between here? That contact force between the two blocks, the normal force, if you will. So the idea is whether we put the force on the left-hand side or whether we put the force on the right-hand side, the same general result occurs, and that is that both blocks will start to accelerate. And because whether you put the force on the left or whether you put the force on the right, you still have the same size of net force and the same size of total mass, you're going to end up with the same size of acceleration, whichever side you put the force on. Now, the contact force is going to be equal to the mass times the acceleration of the block that contact force is responsible for accelerating. So for instance, if I apply that force F to the left-hand side of the big block there, then what's going to happen is the contact force is going to be just enough force to make that small block on the right accelerate the same rate at which the big block does. And if instead I apply the force to the right-hand side, to the small block, then that contact force between the blocks is going to be just enough force to accelerate the larger block at the acceleration of the smaller block. Now, since either way, the acceleration of the blocks is the same, the larger normal force is going to occur when we have to accelerate the larger or more massive object, the big box in this case. And so that happens when we apply the outside force to the smaller block. So the normal force between the blocks will be biggest when the force is applied, the external force is applied to the smaller block. And that is answer B. Number 9. A ball is thrown upward into the air. Ignore air resistance. When it is rising and reaches half of its maximum height, the net force acting on it is what value? So if we were to draw a force diagram for this object, the only force acting on it is gravity. Gravity is always acting on objects, and we don't have contact with any other things. We're not in contact with a hand or in contact with a table, so there's no other forces present. Therefore, the net force is just equal to the gravitational force, which we also call the weight of the object. And that is answer A. Number 10. Two inclined planes A and B have the same height, but different angles of inclination with the horizontal. An object is released at rest from the top of each of the inclined planes. How does the speed of the object at the bottom of the inclined plane A compare with that of the speed at the bottom of inclined plane B? So again, A and B have the same height, but different angles of inclination. So for instance, we're talking about comparing a situation where maybe that's an arrow. I didn't mean to make that an arrow. I just meant to make that a line. My apologies. So one incline that looks like that, and the other incline goes the same height, but it does it in a much sharper angle, for instance. And so we're comparing these two inclines. And because they have the same height, we know that if we place a block at the top of this, we're talking about a conservation of energy problem. And as we've already talked about, when you're dealing with conservation of energy, you're talking about the potential energy at the top, the MGH, being converted to kinetic energy at the bottom. The mass cancels out of these problems almost all of the time, so we don't have to worry about the mass, but also the angle doesn't come into it, because the only thing that matters is the MGH, the height that the object is at the beginning, and then at the bottom that height is 0, we want to know the speed. So since only the height matters and they both have the same height, they should have the same kinetic energy and thus the same speed at the bottom of both inclines. And that is answer C. Number 11. In many cartoon shows, a character runs off the edge of a cliff, realizes his predicament, and lets out a scream. He continues to scream as he falls. If the physical situation is portrayed correctly, from the vantage point of an observer at the top of the cliff leaning over the edge, the pitch of the scream should be doing what? So when we're talking about the pitch of the scream, we're talking about the frequency at which you observe it. And that's a Doppler effect problem. We're talking about motion towards or away from the source of the sound. In this case, what is it? The character. Okay, so the character runs off the edge of the cliff. He's the one that's screaming. He's the source of the sound. And as you stand at the top of the cliff, he's moving away from you. So if he's moving away from you, that's going to be a red shift, not a blue shift. And that means a shift towards lower frequencies and longer wavelengths. Lower frequency means lower pitch. So the first thing you know is it's going to shift towards a lower pitch. Now the next thing is, does it stay constant or does it change? And we know that the frequency observed depends upon the speed that the object is moving away from you with. Now, when you fall off of a cliff, you don't fall at a constant speed. You speed up as you fall, which means the Doppler effect is going to get larger and larger as you continue to fall. So the pitch should shift to being lower, and it should continually get lower as you continue to fall. So lower than the original pitch and continuing to decrease as it falls. That's answer D. Number 12. In terms of impulse and momentum, why do padded dashboards make automobiles safer? So impulse and momentum is our main tool for collisions. And so we're talking here about padded dashboards, and we're thinking this has probably got something to do with collisions. So if you were to have a collision with your car, why would having a padded dashboard perhaps be a little safer than not having one? And the answer with all of these, whether it's seat belts, whether it's airbags, whether it's padded dashboards, all of these safety features come into how long it takes to bring you to a stop during a collision. So by extending the time period during which you are slowing down, you're decreasing the magnitude of the force necessary to slow you down. In other words, you're using a smaller force for a longer time rather than a big force for a short amount of time. And since it's the acceleration, the force, that ends up having an impact on you, that ends up, causing you damage, that's what we're worried about. So what they do is they extend the time of the collision and thus reduce the force of the collision. And that looks like it is answer C. Let me also mention that A and B are incorrect here because it does not change the change in momentum or the impulse to the object. So remember that impulse, the impulse momentum theorem, says that the impulse delivered to you is going to equal the change in momentum that you experience. And whether you have a padded dashboard or not, you start out with the same mass and the same velocity, the same momentum. And whether you have a padded dashboard or not, at the end of the accident, you have come to rest and your final momentum is zero. So your change in momentum is the same with or without the padded dashboard, which means the impulse delivered to you is the same. The only difference is whether the force and time are the same. Force times time has to be the same, but you can have a larger force in a shorter time, or you can have a smaller force and a longer time. So again, the correct answer on that one is answer C. Number 13. Harry and Sue cycle at the same speed. The tires on Harry's bike are larger diameter than on Sue's. Which wheels have the greater angular speed? Okay, so this is a comparison between linear speeds and angular speeds. So just to remind you, linear speeds, we use the letter V to represent linear speeds. And for angular speeds, we use the curly W, the omega. I don't have a curly font here, so it's just showing up as a W. But omega is our angular velocity. And we know that these two are related by V equals R times omega. That's the equation that relates the linear velocity to the rotational velocity. Now, all parts of your tire or of your wheel all rotate with the same angular velocity. But different parts of your wheel will rotate with different tangential or linear velocities. The outer rim of your tire that has the largest radius will always have the largest speed in meters per second. Now, in our case, we know that both bicycles are moving with the same speed. We know that the V for Harry is the same as the V for Sue, which means that when we go to find their omegas are going to be equal to V over their radiuses. And since they both have the same V, the one with the larger radius will have the smaller omega value since it's in the denominator. And the one with the smaller radius will have the larger omega value. In this case, that's Sue. So the correct answer is B. Sue's wheels will have the greater angular speed. What this is really telling us is that if they want to travel down the road at a certain speed, 10 miles per hour, Sue's little wheels will have to rotate more regularly. They'll have to go around more times every second than will Harry's larger wheels. And that makes sense. Number 14. Which of the following is not conserved in an inelastic collision? So let's first talk about inelastic collisions. In an inelastic collision, as with all collisions, as long as you choose the appropriate system, as long as you choose a system that includes all colliding objects, and there are no net external forces, then usually momentum is conserved in collisions, whether they're elastic or inelastic. But the difference between elastic and inelastic was that elastic collisions conserve energy as well as momentum, while inelastic collisions only conserve momentum. So the thing to really look for here is that we're going to lack an energy conservation principle in an inelastic collision. Now, before we jump to the conclusion that this is energy is the answer, let me remind you that when we talked about energy this semester, we weren't really talking about total energy. When we talked about energy this semester, we were talking about mechanical energy. That's kinetic energy plus potential energy. It's that mechanical energy that is not conserved. Conservation of total energy is a universal principle and is always true. But conservation of mechanical energy is only true when there's no non-conservative forces doing work. In other words, it's only true when we don't convert our energy into forms of energy that we haven't been able to talk about in this class. And the only forms of energy we've really talked about in this class are kinetic energy and potential energy. So if it converts that energy into heat energy, that's still a form of energy and the energy is still conserved. But the mechanical energy is not conserved because we don't have a way to calculate the heat energy. And so we're looking for situations where the mechanical energy is conserved or not conserved. All right, so I've digressed a little bit, but what am I trying to say here? In an inelastic collision, total energy is still conserved, but mechanical energy, that is kinetic plus potential, is not conserved. So with that in mind, let's take a look at what our options are. So which of the following is not conserved in an inelastic collision? Is momentum conserved? Momentum is absolutely conserved as long as we've chosen a good system that includes all of our colliding objects. Mass is conserved. We don't generally have anything changing the amount of mass in our system, so mass should stay conserved. And our total energy is a universal invariant. It stays the same. But the kinetic energy is something that changes based on whether it's elastic or inelastic. So the correct answer here is C. Number 15. Two different masses have equal non-zero kinetic energies. The momentum of the smaller mass is what? So again, two different masses have equal non-zero kinetic energies. So if I were to write out the kinetic energies of those two objects, just hypothetically, I'd say, okay, I've got a small mass object and its kinetic energy is going to be 1/2 times the small mass. But in order to have the same kinetic energy as my larger mass object, it must have a really big velocity. So its kinetic energy is going to look something like that. 1/2 small m times big V squared. And I'm going to compare that to the kinetic energy of a more massive object. That's going to be 1/2 times a big mass times a small velocity squared. And again, these two have to be equal to each other because we're told that their kinetic energies are the same. Now, we can see right away that that means that the 1/2s can cancel out and we don't have to worry about them. That doesn't really tell us anything. But what it tells us is that the small m times the big V times the big V again has to equal the big M times the small v times the small v again. That's the equation that we get that tells us how these quantities relate to each other. Now, they want to know how the momentum of the smaller mass compares to the momentum of the bigger mass. And so at this point, I point out that m times v is the momentum of each of these objects. So in order for this equation still to be true, in order for the left-hand side to equal the right-hand side, if this v is big compared to the v on the right-hand side, then the box on the left has to be small compared to the box on the right. So if I were to write these with letters again, I would say on the left I have a small momentum times a big velocity, and on the right I have a big momentum times a small velocity, and those kinetic energies are still equal. But what that tells me is that the side that represented my small mass, the left-hand side, also had a smaller momentum in this case. So in this case, let's see, the momentum of the smaller mass is smaller than the momentum of the large mass. That is answer A. Does that make sense?
Definitely.
All right, and one more concept question, number 16. A light car and a heavy truck, both traveling with the same speed, skid to a stop with the same coefficient of friction. How do their stopping distances compare? Now, there's two different ways to approach this. You can either approach this with forces and kinematics, or you can approach it with the work energy theorem in one step. The work energy theorem would tell us that the work done by friction has to equal the change in kinetic energy, 1/2 mv squared minus 1/2 mv initial squared of the object. Now, in this case, the work is done by friction. And the work done by friction is the force of friction, which is minus mu times the force normal, which is usually going to be something like m times g, and then times the distance. And in this case, since we're ending with zero speed, that's just going to be equal to minus 1/2 m times v initial squared. Okay? Again, I want you to notice that as we do this, the mass is on both sides of the equation. And so again, the mass cancels out. And so what we find is that the distance does not depend upon the mass of the vehicles. The distance that they travel, the d, only depends on their initial speed, and in this case they have the same speed, and it depends on the coefficient of friction, and in this case it tells us they have the same coefficient of friction, and it depends on g, and they both have the same acceleration due to gravity. Therefore, they both stop in the same distance, and that's answer C. All right, I'm going to pause here to stop my recording.